Section 1.3 deals with functions and relations. So a function from A to B is a rule of correspondence that assigns each element of A to exactly one element of B. For most of you in this class, the rule of correspondence is going to be an equation, right? But we learn a little bit later that there are other ways we can express functions, right? So one way we test for whether something's a function is we apply the vertical line test. So the way you test to make sure that every x is only returning one y value is you draw a vertical line and you can kind of scan it back and forth across the graph, and as long as it only ever crosses the graph in one place, then we know that that is a graph of a function. We also, when we talk about functions, we talk about their domain and their range. So the domain is the input values, right? So it's all the values of x or whatever variable we're using as the input variable that are allowed to be plugged in, meaning they're going to return an answer. So if we want to find the domain graphically, we read the function from left to right and we list out all the values that return a y. And here there's a little bit of a typo here. This says find the range. This should actually say domain. Right? If we want to find the domain algebraically, well, what we do is we start with the entire number line, right? The entire x-axis from negative to positive infinity. And it's impossible to check for all the values that do work. So what we do is we look for the values of x that will not work, we throw those out, and then we keep everything that's left. So there's three main impediments that you're going to find, or values that we might have to exclude or kick out. So the first would be any values of x that would make the denominator equal to 0. So if you have a denominator in your problem, you have to check for that. Any values of x that would make any expressions under even roots negative. So most of the time when we say even roots, we mean square roots, but this rule would also apply to fourth roots, sixth roots, right? So we want to make sure anything that would make those expressions negative, we throw out. And the last one is any values of x that would make expressions inside log functions non-positive. So rule number 3, I included on here because I want you to have a complete list, but logs and exponentials are going to come up in exam 2. So we're not actually going to deal with this in this particular review, but you need to be aware that this is coming up, right? We're just going to add it to this ongoing list. The range are the outputs or the y values that come out of a function. So for range, we don't really have a method yet where we can look at the range algebraically. Typically, we read the range off of the graph, and we do that by reading it from the bottom to the top. Now keep in mind, when you express domain and range, we're going to use interval notation to express domain and range, right? And I'm going to do some examples where we explain exactly how to use that properly. So example 3 says find the domain of the following functions. So if I look at this function here, it's a polynomial, and I see that there are no denominators, there are no radicals, right, or square roots. There are no logs in this function. So there's really no reason that every value of x is not allowed to be plugged in here. So in this particular problem, we would say that the domain is all real numbers, or the interval from negative infinity to infinity. We use parentheses around values that are not included, and we'll use brackets around numbers that are included. But for infinity, we always use parentheses because that is not a finite value and we don't know where it stops. The next problem, however, has a denominator in it, right? So we need to make sure that rule number 1 is invoked. So I need to make sure that I can figure out, well, what values of x are going to make this 0. So what we can say is that x squared minus 1 is not allowed to be 0. So then that means x squared can't be 1. And if I take the square root of both sides, on the left I'm going to get x, but just like we did in the problem in the last section, this is going to be plus or minus 1 because negative 1 squared is 1 and positive 1 squared is 1. So now if I draw my number line. These are all the values of x. Here's -1, and here's 1. So what this expression is saying is throw out 1 and -1. And so we usually use open circles. And then we assume that all other values of x are okay. So now when I want to express my domain in interval notation, I just read this number line from left to right. So the domain is -∞ to -1, not included, so we use parentheses. Then we use a union to pick up the next interval, and everything from -1 to 1, not included, is allowed. And then I'm allowed to grab 1 to positive infinity. Part C has a radical, right? There's no denominator, and so, but I do have to make sure that this square root, this expression, is not allowed to be negative. So what I'm saying now is 2x minus 5 must be greater than or equal to 0. So it is allowed to be 0 because you can take the square root of 0. But if for some reason this radical were in the denominator, if this were 1 over the square root of 2x minus 5, then I would have to exclude 0 because rule numbers 1 and 2 would be invoked at the same time. So those rules can be combined, right? But it is perfectly okay to take the square root of 0. It's 0. So now let's solve this inequality. So 2x is greater than or equal to 5. So x is greater than or equal to 5 halves. So if I sketch this out, there's 5 halves. Now, x is allowed to be equal to this. So I close this in. I'm going to keep 5 halves. But this says x is bigger, right? Greater than or equal to this. So I shade all the values to the right. So now when I read the domain from left to right, I use a bracket for 5 halves because it's allowed, and we accept all the values from 5 over 2 to positive infinity. So let's look at part D. D has a denominator, and then in that denominator, there's a radical. So if I look at just the radical, right, square root of x, well, the square root of x, in this case, has to be greater than or equal to 0. And I know it's allowed to be 0 in this case because the radical doesn't include the -7. It's only over the x. So if I were to plug 0 into this function, I would just get -1/7. That's totally okay, right? But I also have to make sure that the denominator is not equal to 0, the entire denominator. So the square root of x minus 7 cannot equal 0. X by itself can, right? But the expression cannot. So now we're going to solve this, and I get the square root of x cannot equal 7. And note here, I'm going to square both sides. So the only time I have to worry about the plus or minus situation is when I'm taking the square root, right? But this time I'm squaring both sides. So x cannot equal 49. So in our domain, we have to make sure that both of these things are true. So this is where when you have two rules, sketching the domain before we write it is really, really helpful. So there were two numbers that we have to look out for here, 0 and 49. And 49 is a little bit easier to take care of because all we're saying is kick it out. 49 is not allowed. But over here we're saying, well, x can be anything greater than or equal to 0. So we're allowed to keep 0, so I shade in all the values to the right except for 49. So what we're saying here is if any piece of the function kicks a value out, it's out for the entire function. So now I've sort of reconciled these two ideas right here. And so if I write out my domain, it's 0 included to 49, 49 to positive infinity.